All right, everybody, welcome to our lesson video here for 1.2. We're going to be examining the graphs of functions. So in part one, we're going to be focusing on finding the domain and range of a function graphically. We already kind of gone through how to do that using algebraic techniques. So just some quick things to be familiar with here. The graph of a function x is simply a collection of ordered pairs f comma f of x such that x is in the domain of f and f of x is in the range. So a lot of things going on there, right? All of our points are going to be x comma f of x. I'm not sure. That's a little bit of a typo there. But what we mean by this is, so if you pick a point like this one right here, where the coordinates of this point are 3 comma 6. So 3 is our input into our function, 6 is our output given that input. So if we were to take our function, which is right here, this absolute value function, actually evaluate it, f of 3, the output is going to be 6. And that's what every single point on this graph is. And we'll just quickly show that that works for this one. In here, inside of our absolute value, we just get 0. So this is negative 0 plus 6, right? And we get 6. So every single point on our graph represents an input and an output pair for a given function. For graphs, we may know the equation that creates that graph. We may not know the equation, but that's what's happening with our graph. Clear this and move forward. Another thing here, just to kind of keep everything so that we're all having kind of common language and understanding of this. So when we talk about the x value, the input, we're talking about a distance from the y-axis measured along the x-axis, right? So wherever we have a point, let's just say, my fault. Draw this. So we have a point right here, right? This point has an x coordinate, right? The x is -1, and that's distance can be measured from the y-axis, 1 unit from the y-axis, and it's just simply measured along the x-axis. Same thing over here, you know, we pick a point somewhere, whatever it is, this point down here, right? This unit is 2 units away from the y-axis in the positive direction, so its x value is 2. And then similarly, the y coordinates can be measured as a distance away from the x-axis. The y coordinates in our case may also be called f of x, right? A function given an input, the output of a function given an input of x. And anyway, this one is 3 units below that. So, right, we get a -3 for the output in that case. All right. Some graphs that we're going to be looking at may have their domains restricted. Maybe that's for context of a word problem or just because we feel like doing it. And so in this graph, you'll notice that there are these open points. There's an open point here, or sometimes we also call this a hole. So the function is defined all the way up until that point, but at that point is actually undefined. Whereas over here, we have a closed point, and the function is defined all the way up to and including that point. So just kind of a small difference, you know, you want to pay attention to some of these endpoints, whether we have a hole or a closed dot there. If there's no endpoint and the graph kind of runs off the screen, we're just going to assume that it's going to continue forever. We won't always have arrows drawn on those, so we'll just have to make that assumption. All right, a couple quick definitions. Domain. So when we talk about domain graphically, we're talking about the spread of the x values on the graph from the farthest left to the farthest right. And the range has a similar thing, the spread of y values, but from the lowest point to the highest point. We're going to be writing these domains and ranges in both set notation using inequality symbols and also interval notation. So, you know, we may have something like this in set notation. I don't know, just making something up, saying that the x values go from -1, including -1, all the way up to 5, or we may get something like this, right? Interval notation for the same thing. Some things that we do really need to look out for when we're especially examining the graphs to figure out domain and range are any types of what are called discontinuities or breaks in our graph. So endpoints, a part where our graph just sort of stops, which can happen on certain types of graphs. Holes, so places, specific points where our function is undefined, or even vertical asymptotes, or horizontal asymptotes for that matter. So we'll kind of try to make sure we notice all those different things and what they look like on the graph. All right, so let's go ahead and take a look at this one. First example of finding the domain and range from our graph. So the domain is from the farthest left over to the farthest right. If either of those are, we don't have a farthest right, it keeps going to the right forever, or keep going to the left forever, and we may use infinity or negative infinity. So here, I think it's pretty obvious to see that our graph stops, right? It has this endpoint, doesn't go any farther left than this point here, -5. And but it does keep going to the right forever. So we can always sort of assume that, even if there's not kind of an arrow drawn like that. Or if we graph this on our own and kind of zoomed out on Desmos, we could kind of see that that's what's going on. So anyway, our farthest left, or our minimum x value for our graph, is going to be -5. And there is a point there. That point is included. So if we're using interval notation, we'd want to go ahead and put a bracket with that. And then the graph goes to the right forever, so it has no maximum x value. It keeps going to infinity. And so that is our domain. Similarly, we could write this using some set notation or inequality symbols. We can say that our x values must be greater than or equal to -5. Okay, that's another way for us to communicate this interval using inequalities. And that's for the domain. Now, the range in this case, the range is from our lowest value all the way up to our highest value. And so here, I think we can kind of see that we do have a lowest value. The graph does not go any lower than this right here. And there's a point right there. It doesn't go any lower than -3. So -3 is our lowest value. And there is a point on the graph at -3. So that is an included value. And this can be a little tricky. It can be sort of hard to determine whether the graph is going to be going up forever. It is. It will go up forever. If we input a sufficiently large x value, we will be able to get any output that we want as high as we want. The x's just will have to be very, very large to make that happen. So it's going to be going up to infinity. Similarly, we could write this using inequality symbols. So we can say that the y coordinates must be greater than or equal to -3. Right? Has to be greater than, has to be higher than that value. And that's our domain in red there and our range in blue. Let's go ahead and move forward and take a look at some other graphs, some other things that we may see. All right, so here we have a parabola, a basic quadratic equation. It's a good one to take a look at. We don't know the exact equation for this one, though if we know enough about quadratics, we could probably make some guesses. It's kind of interesting. Is there a farthest left that this graph goes? Well, it's sort of hard to tell. I did kind of say that whenever we're looking at a graph like this and it runs off the screen, we have to sort of assume that it does continue moving in the direction that we see there. So if we have these kind of arrows going on at the ends, we can kind of assume that it is kind of moving down and to the left and down and to the right forever, which means that this graph has no farthest left value, no minimum x value, and it has no maximum x value. Looking even deeper, there are no holes, no asymptotes, no type of discontinuities present. So when we go to write the domain for this one, this graph is from -infinity all the way up to +infinity for the x values. Using set notation, there's not really an inequality way to write this, but we may see someone explain this as being all real numbers. That's being our domain. another completely valid way to write that. Okay, next, the range. So again, the range is the lowest value all the way up to the highest value. And so since this graph is going down forever, there is no lowest value. But we do have a highest point, right? This graph does not get any higher than this value up here at 9. So the lowest value for a range is negative infinity, right? Goes down forever. We always use parentheses with negative infinity, and it goes up to positive 9. That's the highest value. So the graph goes up to positive 9 and doesn't exceed that. Yeah, but there is a point there, so it must be included, right? That is a point that is part of our range, so it is included. Now, just like before, we could write this using some inequality symbols. So this says that our y values must be less than or equal to 9, right? Y coordinates that are at 9 or lower are valid or are allowed. All right, let's keep moving forward. Find the domain and range. Okay, so here we go. We have another equation. This looks sort of like a cubic or third degree polynomial. Oh yeah, we can actually see the equation. We're given the equation this time. Knowing the equation is a really useful thing, right? Especially when we talk about the domain and what numbers are allowed as valid inputs, right? Because we know there are certain things that we would be looking for if we were trying to find this domain algebraically, right? We'd be looking for square roots, anything that would cause us to divide by 0, those sort of things that are going to cause restrictions. In this case, there's nothing, right? None of that going on anyway. It's just a simple polynomial. There's no value of x that we could plug in here that would cause some type of an error, either taking the square root of a negative value, which we know is not a real number, or causing us to try to divide by 0 or something like that. So knowing the equation, very useful. Our domain is going to be from negative infinity to infinity, or all real numbers. We can also see that graphically. This graph is continuing down and to the left forever. There's no farthest left value, so our minimum x is negative infinity, and it is moving up and to the right forever. So there's no farthest right value, no maximum x value, which would make that maximum infinity when we go to write this. And again, we could say that that's also all real numbers. I'm just going to leave it in the interval notation though. All right, and then the range is the lowest value and the highest value. Similarly, this graph is going down forever. There is no minimum value, and it's going up forever. There's no maximum value, and it hits everything in between there. So our range is negative infinity to infinity as well. Kind of cool. Both the domain and the range are all real numbers. Okay, and let's move forward. Last one here. We have a nice circle. Looks like a circle anyway, centered at looks like 2, 0. Oh, and we also have the equation here. So yeah, that's the equation of the circle. This equation is not a function. We can kind of quickly see that it would not pass the vertical line test, but that doesn't mean we can't express its domain and range. If we want to think about it as x being our input, y being our output. So the domain is the farthest left to the farthest right. So farthest left this graph goes is here at -2, right? You can see that. And then the farthest right this graph goes is over here at 6. So between -2 and 6, and that's our domain. And again, we can write that in interval notation from -2 to 6 using brackets for both sides here, because there is a point at each of those values and for everything in between. Or we could write that using inequality symbols. So from -2 all the way up to 6, including both of those ends, we use the or equal to symbols with that. So this one telling us that x has to be between these values inclusive. All right, and then our range, very, very similar here, right? We can see our lowest point is down at -4, and our highest point is up here at 4. So the y values fall in that range. So from -4 the lowest up to 4 the highest. Or similarly, we can write that out using inequality symbols. we're using brackets and we're using or equal to symbols because there are actual included points as part of our graph at those specific values. So they are included in part of the domain and range. Yeah, looks great. All right. I'll see you guys in part 2. Actually, apologize. There is one final one. Let's sneak this one in here. This is actually, you may recognize this graph from earlier. I thought I would throw restricted domain graphs here. So we can see that it's only graphed from -1 to 4. We have these nice endpoints. So we can see the graph stops at -1 on the left side and 4 on the right side. So that helps us really easily find the domain. We do need to be careful about the open dots versus closed dots, right? So it is included over here at -1. This point is part there because we have that closed dot, whereas here we have this open dot, so it is not included. So when we go to write this side of our domain, our maximum x value, it's not included. The graph goes all the way up to 4, but not including 4. All right. And then for the range, we go from the lowest to the highest. A lot of people are tempted to just look at the endpoints like here and here. But the second one, that is not the highest. The graph goes well above that. So we want to go up to the highest points, right? That may not be the endpoint. Same if it was the middle as well. But highest is at 4. The lowest is at -5. So our graph exists everywhere in between those, right? Even at 0, even though there's a hole there, it is defined right there. So everywhere in between it. So our range would be from -5 to 4, inclusive of both ends. Those are both brackets. All right, I'll see you in part 2 now, and